Good afternoon, gentlemen. First off, I'd like to thank this board for taking the time to hear my proposal. Now, we've all heard the legend of Atlantis, a continent somewhere in the mid-Atlantic that was home to an advanced civilization, possessing technology far beyond our own, that, according to our friend Plato here, was suddenly struck by some cataclysmic event that sank it beneath the sea. Now, some of you may ask, why Atlantis? Pure fantasy. It's myth, isn't it? Well, that's where you're wrong. Excuse me, gentlemen. Hello? You're telling me this is not Disney's 2001 Atlantis The Lost Empire and is instead the History of Math final presentation? All right. Well, is that better? Okay. Well, I suppose this is not how we expected to be here today, but here is my final History of Math exam, which is math and knitting. Thank you all for being here. Cedric, so nice to see you. And Melanie, so great to see you as well. So glad you could be here. I hope you enjoyed this very illuminating topic. Now, what am I going to talk about today? Well, I'm going to be talking about the connections between knitting and mathematics, but precisely answering the exam question, which is how do mathematicians like Lobachevsky differ from Euclid? So the first thing that we're going to go through today is, what is knitting? Then the connections or the non-connections between knitting and math. Then I will draw between Euclid and Lobachevsky and talk about hyperbolic space in knitting and crochet. So what is knitting? Knitting, I have an example here, is the process in which you have two needles instead of the crochet's one, in which you continuously add or subtract stitches in order to make a pattern. That's not the right way to go. Essentially what you're doing here is you follow a pattern that tells you to knit or purl, which are basically very similar stitches that just provide you a different pattern. And you continue on in order to make different shapes or different articles of clothing, or whatever. So how does this relate to math? Well, firstly, knitting and crochet are some of the earliest mathematical or homeware that involves the act of counting, right? Because you have to ensure that you're counting the right number of stitches every time, or else you're going to either lose a stitch or add a stitch. Now, how on earth does this, even if you're counting stitches, how does it relate to mathematics? Well, an interesting thing to consider is when you have two sticks, for example. And if you have 3, 6, 7, if you have 8 stitches on one needle, then that means that to get it onto the other needle, you should have 8 stitches, correct? Well, not always, because you can always add or subtract stitches, which essentially means that even though your left hand needle has 8 stitches, if you add a stitch onto the right needle and you do the row, instead of having 8 stitches, as you might imagine, you get 9. Now, while there's plenty of research out there about knitting and mathematics and how to create knitting patterns through algorithms, what there isn't really anything on is about how exactly you do the mathematics that allows you to understand where exactly you're getting or how exactly you create the pattern to add. I didn't do this correctly. 9 stitches, 3, 6, 7, and then 8, 9. I did something very wrong here. So basically, what is knitting? Knitting is taking 2 needles and creating knots in order to create forms, as I said. But here's the issue, is if in a pattern, for example, a pattern, for example, might say you have 90, how many stitches did I end up? I had 99 stitches on my left hand needle, right, on this left needle. And if the pattern tells you, if you have a pattern that is like 8 stitches, so you have, say, knit, which means taking 3 of those stitches, moving them over to the right, knit 3, and then you have a repeat here, which might be purl, which is again basically the same as knitting, and then you have an added stitch, you have a knit, you have a slip stitch, which means that you just subtract, you basically like, you just move one of the stitches from the left hand side over to the right without doing anything with that yarn. You do another knit, and then you do a pass that slip stitch over, so you lose that stitch. So, and then let's say this one. So this pattern here, this P2, YO, K1, SL, K1, PSSO, K1. What does this mean? This is mathematics. Why? Because what it's actually telling you is to add 2, add 1, but I'm going to put this in brackets because it's special. 1. You like, and when I say add 1, I mean you're losing the 1 from the left and you're putting it onto the right needle. You add 1, you add 1, and then the pass slip stitch over, you'll lose 1, you add 1. So essentially, what you have here are 2 different, like, or 3 different categories of addition and subtraction, because these 2, 1, 1, 1, 1 were stitches that were already on your needle. But here's the thing, this one here and this one here, this one didn't exist on that left needle. This one only exists on the right needle. That would be like saying, if I can algebraic eyes this, would be like saying you have an equation that looks like 2 plus 1, and then you have 4. That doesn't make any sense, right? So a thing that you have to consider about knitting is the fact that it seems like it would be an equation. It seems like it should follow that, like, one thing goes over to the other side, but that's not the case. However, what you could consider then is saying that this plus 1 might be something like 3, and then you add something that's not in the normal numbers. Perhaps you could add, let's just say, I. Because technically we know that I exists, but you know, I don't know how this math works. That's the issue here, right? You can understand how this is kind of confusing because you have an algorithm that means, or you have an equation which might imply to you that, like, when you're knitting, okay, you have 8, maybe you add 2, but where do you add them, right? Okay, so then your algorithm is like every third one, add 1. And then you continue on with a different part of the pattern until you lose 1, subtract 1. how does that work? So while a lot of like knitting patterns, like you can create your own knitting patterns online by like doing an algorithm, sure, all it does is it just spits out this part. It doesn't actually tell you what's happening here. And it seems to me like this implies like some sort of mathematics is going on. It seems like the most basic form. You take one and you move one over, you know. Take one, move one over. You take one, you move one over, right? And yet, how do you create an equation? Well, one of the ways to solve these problems, for example, would be by doing substitution. And again, this has nothing to do with what we've talked about in class yet, but we're getting there. So I had a problem when I was knitting, which was why I'm here talking about knitting today, which is that I had 99 stitches on my left needle. And I had 96 stitches after I started it, but before I began the repeated pattern, as we've already discussed. So I knew that my pattern required a certain amount of stitches, as I showed you, from my left needle to use that pattern. And that showed me if I divided 96 by that number 6, which was the number of repeats, I had 16 repetitions, right? And if I added 2 to my pattern, which essentially means like the net of this pattern was +2, which basically means like I had 2 yarn overs, which adds a stitch that didn't exist in the beginning, right? Because all of these K1, whatever, P1s, all of these already existed, those 2, right? So those don't really count because what they're doing is they're subtracting from the left hand needle. This is the left, this is the right. They're subtract this K1 and this P1, that is already there, right? So those stitches already exist. I have 99 stitches on this left hand needle. I need to get rid of those 99 stitches by moving on the right side, right? I need to have no more stitches on my left hand needle. I need to have all of those stitches on the right hand. And if I have a pattern that tells me that I'm using like say 6 stitches from the left hand needle, but I'm adding 2, that means that those extra 2 stitches didn't exist on my left hand needle, but they now exist on my right hand needle, which then gives me 32 stitches if you multiply 2 by 16 repeats to give me a total of 131 stitches on my right hand needle. But here's the issue. If there are 16 repetitions and 131 stitches on my needle, then the next pattern after this, so it's not just like you keep it here, you continue on, and then the next pattern after that tells you that there are 131 stitches, and then the beginning and the end of the stitches is 11. You have 131 stitches. Minus 11, you have 120 stitches to get that pattern. 120 divided by 15 repeats, because then, so this doesn't make any sense. It's all gibberish. Trust me, I spent like an hour writing out this math. It was very confusing because what I was trying to do was trying to figure out a way to understand how many times I needed to repeat the pattern while grappling with the fact that my left hand needle and my right hand needle did not equal each other. And I basically came up with this equation, which was that the original, oh, that's not the right one. Oh, the original equals B plus PR. This means anything that's not in the pattern, so the beginning and the end. This means the number of pattern stitches. This means the number of repeats. And this equals the original number of stitches on the left hand needle. Now again, I feel like none of this particularly matters in the term of what we've been talking about in the course. And this is all just a bunch of gibberish again. But the issue I hope you can see is that it is very confusing and strange to be looking at something so simple of just two needles that can create such difficulty in mathematics. And if you can tell me how the heck algorithms work in order to tell you when to add something to the left-hand side, please tell me, because I really want to know. So let's move on, because I've already been talking and ranting about knitting for far too long, and get finally into this question and into Euclid versus Lobachevsky. So basically, as we saw in class, Euclid created basically the most seminal, important piece of work in mathematics for the last 3,000 years, which has influenced everybody, which has told us about all of the rules and all of the basic like foundations of mathematics, right? We know that like the sides of the angles of a triangle will equal 180 degrees. Euclid, right? Euclid, however, also had a theory of parallels. So as we know, in normal mathematics, when we have a plane, say this nice glass, you can have two lines which are, again, parallel to one another, and they will never reach each other. They will never cross each other. They will never do anything. This can be particularly seen through Descartes' method of like graphing and the Cartesian coordinates, which is obviously, as we know, x and y. You have like a coordinate here and a coordinate here, or actually that's not going to be good because you're not going to be able to find the slope. If you had a slope here and say it was like 3x plus 2, and you had something here and it was just 3x, and you were to like do the math here, 3x and then 3x plus 2, and you were to try and find when they would reach, you're not going to be able to find an answer, because the way that this mathematics works is that you basically have the same line but like raised up by 2, and that means that those are parallel because they have the same slope. They will never intersect each other due to math that I don't really want to go through right now. I think we all know that that is true. However, Lobachevsky and other people within the 19th and 18th century decided, sure, but like, could there be spaces that don't abide by Euclid? And that's where kind of Lobachevsky, Poincaré, all those people come in, because they created the idea, or they found the mathematics that helped explain non-Euclidean space, or also known as like hyperbolic space. And essentially, if we see like Poincaré's circle, you have like a star here. Poincaré said basically that a hyperbolic space, or a non-Euclidean space, meant that this star here and this tiny star here were the same size. Does that make any sense? Not really. Can you really visualize that? No. Lobachevsky, on the other hand, decided, I'm not going to do this whole circle thing right now. But what he was going to do is he was going to go back to this whole Euclid parallel thing. He was going to change things up. Because what he showed then was that one line here, right? If you had another line up here, and you had these two lines, these don't look parallel to this line here. But Lobachevsky proved that indeed these lines are, because what he is showing is, for example, like on a sphere. On a sphere, for example, like if you have a line here or whatever, there's a whole bunch of like things that could go through that. That's not fully correct. But the whole point is, like, when you look on like a sphere, for example, you know that you can travel in a straight line and then reach the same exact point multiple ways, right? So that was kind of like the foundation for like non-Euclidean space. because what they saw is like, well, if a line is meant to be the shortest distance to another point, is there a time when it seems like it's not a straight line, that it could be like the closest way to a point? And that's where this comes in, because Lobachevsky and his other pals who created non-Euclidean space and mathematics demonstrated that essentially, if you have like a sign or an arc basically on like a non-Euclidean circle, and you have a point here and you have a point here, it is not a straight line that will be the shortest distance. Instead, it will be what appears to be the curve that will be the shortest distance. Now, how does that work? Well, guess what? That curve, not actually a curve, it's a straight line. What? I know, confusing. How the heck did anybody understand this? I don't know. But guess what? There are things in this life that sometimes reveal to us very wacky things. So, I should have thought that up. I'll leave everything else up. Now we turn to the purpose of the incorporation of knitting and crochet here. So, I have a couple examples of what I would call Cartesian or Euclidean knitting, which is basically this, right? You have the same amount of rows every time. You know, you could point to a point, and then you could show another point, and you could draw a straight line, and that is going to be the closest way of getting there, right? This is, if you ignore the fabric like rolling, this is a straight plane. Let's just call it that. It's a straight plane. This is a better example because if you look at, I might say so myself, the very nice stitches on this top here, you see that even though it curves in, it's still flat, right? Because what's happening here is it's still on this type of Cartesian plane, right? So this measurement might be like 5 inches, and this might be 7 inches, but it's still flat, right? It's not, you could say part of this is 3-dimensional, but for the ease of this, we'll just say that this is 2-dimensional, right? This is a 2-dimensional surface in which it abides by the Cartesian like representations of mathematics. But here's where it gets wild, all right? You can take knitting and crochet and you can demonstrate hyperbolic space. Yeah, all that stuff that was very confusing to understand, you can do it. I learned how to crochet out of like, I don't like to crochet. I hate crocheting. I don't crochet. But what I did for the purpose of this class is I learned how to crochet the most basic thing. And I learned how to crochet hyperbolically. So I have a couple examples of hyperbolic stuff here, and I'll go through them in detail. And I have a very special one here, which I will explain in interesting ways, because I'll explain why I hate crocheting. Crocheting, I've talked about knitting taking 2 needles. Crochet takes 1 needle. Here's the interesting bit. So you take crochet, I have one here. And what you're doing here is that instead of having all of your stitches on the needles, right? You have all the stitches here. What you have with crochet is you have all of your stitches below your needle. And so then what you're basically doing is you're going in, and every time, you're essentially just making insertions into these stitches, which is what you're doing in knitting, but with 2 needles instead. So you would think, oh, well, if I can do something with like 2 needles, I should be able to do it with, well, if I can do something with 1 needle, I should be able to do it with 2. Isn't that right? Right, you can see this. Well, guess what? That's not really how it works, which is very confusing and raises several interesting implications about how exactly mathematics can connect to these kind of fabric arts. So I learned how to hyperbolic crochet, and essentially what you do is you take your crochet, which again keeps falling out, and you start with like a certain amount of stitches. So this one I believe starts with 7, and then after you're doing a pattern, so say for example you're gonna crochet one normal, crochet another normal, and then on that third repeat what you're going to do is you're going to crochet twice into the same stitch, and then you're going to do a normal one, and on that third one again you're going to crochet twice into it, like you're going to do 2 single crochets into the same stitch. And you'd think, that shouldn't really make like any big difference, right? Like if you're just increasing by every so often, what's that going to look like? It's going to look like hyperbolic space. So I'm going to lay some of these out to my beautiful audience, and we'll go through them. So I should not have chosen purple for this because my carpet is very dark. But what you have here then, this one's the best one to explain what the hyperbolic plane is. In 2 dimensions, technically, right? Like all of these are literally just one thing, you know, they're just one row of stitches each, like, but then when you put them down, they don't really, like, they kind of ruffle up, right? This one certainly ruffles up. So even though this is 2-dimensional, it's abiding and squishing into 3 dimensions. So the, like, Lobachevsky basically says, like, that if you have a point here and you want to get to a point here, the quickest way to do that is not by going across this surface, but instead arcing from here to here. Because if you're to cross a straight line, you're crossing all of these bumps, I believe. That's my understanding of Lobachevsky. But also, here's an interesting thing. Every time you try and learn hyperbolic space, you're learning it like in this way, like with circles or with like really weird like postulate things, right? And the thing is that you can't even find a way to create a hyperbolic plane like by coordinates. Like you can't tell, like I have not found anything online that tells me, okay, to create like a hyperbolic like space, what you're gonna do is you're gonna have like 4, where am I? Like I've seen nothing that explains to me how you go from like 1, 2, 3, 4, and then 1, 2, 3, 4, 5, 6, for example, and then like, right? So basically if you were to, let me just do this mathematically and explain it. If you were to have 4 spots, right? And then you were to increase every, say, every second one, you would have 6 at the end of that row after you have 4, right? If you were to then increase again, every second one, so 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2. Then in this row, so you have 4 here, you have 6 here, you have 3, 9 here, and then you have 1, 1, 2, 1, 1, 2, 1, 1, 2, 1, 1, 2, 1. That's 3, 6, 9, 12, 13. Right? So you're basically increasing technically by 1 every time. But here's like, but essentially what you should be doing is all of these points, all of the distances between these points in hyperbolic space, from what I understand, these points here and the points between here are the same size. Even though what you're doing here is that you should be squishing them into the same amount of space. So this, I believe, should technically look something where it's like straight down, right? And this is what it should look like. Maybe that's my understanding of it. But essentially, like if you look at these other examples here, right? So in this one, I increased more often, or I increased the amount of stitches per like every 2 increase or whatever. So for this one, I increased every stitch by 3, I believe. Or no, every stitch by 2, and this might have been increase every stitch by 3. So you see, for example, this one, in which I made a circle, that is very interesting. Because you have what seems like a flat circle, which then spreads out to what also seems like a circle, right? You can see this radius, or you can see this circumference here, but which has all of these extra thingamabobs in here, right? And basically what non-Euclidean space says is that all of these points are saddle points, which is basically that like this point here follows the shape of a saddle, right? So this point here and like this point here, you know? So you can see then how each point, no matter where you are, forms essentially a saddle stitch or a saddle point, which again, can't explain to you because I dropped out of math, but that is at least what hyperbolic geometry implies, that every point has a saddle point. So this is crocheting. This is by one needle only. And I thought, well, why can you only do it with crochet? I saw nothing on how to like hyperbolic knit. Why can't you hyperbolic knit? I was like, well, shouldn't you be able to? Indeed. Turns out you can. But do you want to know what it looks like? So for example, I believe this one is only 1, 2, 3, 4. This is only 5 rows of stitches. This is how big it is. This is what my knitting looks like when I tried it. This knitting here has 5 rows of stitches, right? So this one has like a longer beginning. I think it's more like this, or I don't have the other one, but it looks like this. And what you can see here immediately is a difference between, firstly, like how loose this is and how like manipulating, like how much you can manipulate this, right, to this, which is so tight and tiny. And here's the issue with knitting, or yeah, with knitting hyperbolic space, is you can do this. But by this row here, I was so tired of knitting this because you had all of these stitches on your second needle. So in knitting, for some reason, or well, for an obvious reason, what you're gonna do when you have a hyperbolic space is you're gonna like basically almost exponentially increase your amount of stitches, or you're gonna increase your amount of stitches every single time. So this one, I double knitted every stitch. So that means that every time I did a new row, I started with 7 here. That means that every new row I had then 14 and 28 and 56, and you can continue on. And eventually you would see that that would become a problem for a knitting needle. And yet for crochet, which has only one needle and one implement, you have it just hanging down and you can create these types of things with ease. So I was like wondering, I was like, what is this connection between one implement and 2 implements? Can you do things, or can you do like mathematical like equations with 2 like needles or stitches, or like pencils or computer programs or algorithms that you can or cannot do with only one, right? And I don't have an answer to that, but I think this here and this raises some interesting questions, and the whole knitting mathematics problem raises some interesting questions about how the heck we conceive of like one pattern or one thing, one tool versus 2 tools. So what does that mean then Well, essentially, how do mathematicians like Lobachevsky differ from Euclid? Is basically Lobachevsky's only thing that's different than Euclid. He agrees with everything else. Is just about this parallel postulate, which again, he tries to show through this way, or like Poincaré does his weird circle. But indeed stuff like this, crocheting and coral, for example, and like real world like examples of hyperbolic stuff, seems to be the easiest way to understand mathematics, or seems to be the easiest way to understand what the heck hyperbolic space even is, right? And yet what we see in like, or our perceptions of mathematical art or knitting, which is considered like a female domain, is considered entirely like useless in a lot of domains. People don't think of knitting or crocheting as like worth anything. And yet what we can see here is that we can do something that mathematically represents like hyperbolic space, and this is the only way you can do it. You know, like you can make it on paper, but that doesn't really like give you paper. You have to do it by triangles, right? You make a very like choppy example of hyperbolic space. But this, you have a continuous thing in which you see the way the hyperbolic space works, right? And so knitting and crocheting, even though knitting in this case doesn't work very well, like demonstrates that people who are working with these tools and these implements have clearly been like understanding at least the basics or the underlying assumptions of these types of spaces before, because there's so many patterns that include ruffles that look like this, you know? And even if people aren't understanding, you know, Lobachevsky's parallel postulate difference, what they certainly are doing is showing that they understand how the heck to change space, to go from looking like this to looking like this. And I don't have a knitting or a crocheting one because I don't like to crochet, but you can imagine something flat like this, going from flat to hyperbolic space. So that's my attempt to understand how mathematicians like Lobachevsky differ from Euclid using math, knitting, and crochet. Thank you.